So, welcome all of you. In the last class, we started discussing about heteronuclear correlation experiments, where I introduced Heptanol experiment, direct correlation between heteronuclei and the proton. Since it is time consuming, I also said we can do inverse experiments. They are in HSQC, HMBC, HMQC, like that, several such experiments. What is done in these experiments is the magnetization of proton is transferred to X nuclei or any abundant spin to dilute spin. It is taken back from the dilute spin to abundant spin, and abundant spin is detected by decoupling the heteronuclear spin. In the process, what happens is we will come to know the information about the nuclei or the dilute spin which is attached to abundant spins. We can get the correlation information. So, and this is fast, actually it is saving a lot of time compared to the direct detection experiment, because the enhancement of the signal intensity goes by the ratio of the gamma. For example, if you do nitrogen 15 proton HSQC, about 10 times enhancement is there. Carbon 13 proton, about 4 times enhancement. So, a 4 times enhancement results in this enormous saving of the experimental time. Direct detection experiment take about let us say 10 to 15 hours, whereas inverse experiment like HSQC, HMBC, etc. will hardly take less than an hour. In the present day spectrometers, it is all very well set. And also I told you there are several HSQC experiments possible. You can have the decoupling in the direct dimension, or decoupling in the indirect dimension, or decoupling in both the dimensions, or not decoupling in any of the dimensions. Varieties of examples are possible, and I showed you how we can do that. In all these HSQC and HMQC or HMBC experiments, major drawback is the signal coming from 12C attached protons, or for example nitrogen 15 HSQC and 14 attached protons. This is a strong signal which we need to suppress. There are ways of suppressing this, either by using a phase cycling. Once we use a 90 plus X, other is 90 minus X experiment. I showed you how we can do that. And then we can do phase alternation like that and do by phase cycling. Otherwise, we can use gradients, and I also showed you how we can apply the gradients. What should be the ratio of the gradients? Gradients ratio should be 1:4 for proton carbon that we calculated and saw, and for the nitrogen 15 is 1:10. So, with this we have understood quite a bit about inverse experiments. But we need to know how we get the peaks, how do we interpret the peaks. We will start from that from today, about cross peaks in HSQC. Okay, this is, we will discuss about cross peaks, what are the types of cross peaks, how do we interpret the cross peaks in HSQC. Consider a hypothetical molecule like this. We have Ca and Cb are the two groups. Carbon A attached to proton A, carbon B attached to proton B, and this one bond coupling is J, CbHb, this is CaHa. It is very well known. It is a simple hypothetical molecule I have chosen. Now we can think of two different types of isotopomers for this. One is a situation where this carbon A is in carbon 13 state and carbon B is in carbon 12 state, and we have only J coupling for this and it is not there for this. Whereas if I consider another isotopomer, we have carbon 13 here and carbon 12 here, and we get one bond carbon proton coupling we can see there in this isotopomer. And interestingly, in both these isotopomers, we can expect are present only in 1% of the molecule, each of them. This we discussed, remember when we discussed about isotopomers, varieties of things, when we try to interpret the carbon 13 NMR. So, this is each of these isotopomer is 1% of the molecules. Okay. Let us take the hypothetical molecule and see how does the F2 coupled carbon 13 proton HSQC spectrum is seen. Remember, I am telling you F2 coupled, coupling in the detection dimension. Indirect dimension is other one. Okay, we have seen. HSQC cross peaks pattern, how do they come? For example, if I take this isotopomer, I said there are two isotopomers, we will consider this isotopomer. For this isotopomer, in the F1 dimension, we get chemical shift of A. Okay, as I told you how to interpret the HSQC and a Heptanol experiment, if you have there is no diagonal and there are no cross, this of course there is no symmetry here. and diagonal is not this, cross peaks are not symmetric. Take one cross peak, go horizontally and vertically like this, and you are going to get the proton chemical shift here, carbon 13 chemical shift here, or vice versa, one of them. So let us consider this is the F1 dimension and this is F2 dimension. So in the F1 dimension, I get the carbon 13 chemical shift for A. Same if you go in the vertically up, in the F2 dimension, you are going to get proton. So this is F2 is proton, this is carbon 13 here, all right. This is for, and it is going to be a doublet because this carbon is in carbon 13 state. As a consequence, it is going to be a doublet, which is given by one bond carbon proton coupling. We will go to the next isotopomer. Next isotopomer is this. In this isotopomer, what happens? In the F1 dimension, we get carbon B chemical shift. In the F2 dimension, for the same cross peak, we get proton chemical shift. Again, it is a doublet due to one bond carbon proton coupling, because remember I am discussing F2 coupled HSQC. We are not doing any decoupling. And let us see how the spectrum is seen for this molecule. This is the molecule I have chosen. As I said, first isotopomer. Remember carbon 13 NMR spectra, I told you it is superposition of spectra for each isotopomer. First consider the one isotopomer. For carbon 13, this is Ca is carbon 13. As I told you, in the carbon 13 dimension, we get chemical shift. Draw horizontal line, you get a chemical shift of carbon A. From this, as I told you, this carbon is a doublet because of one bond proton coupling. This is one bond doublet, and that is going to give you separation is one bond JHACA. This separation corresponds to one bond JHACA. But remember, if this is the carbon dimension, this is proton dimension. Center of this correspond to, center of this doublet correspond to proton chemical shift. And this is what we have been seeing also, we discussed also. This is nothing but the carbon 13 satellites in the proton spectrum, which has, because carbon is coupled to proton. So this separation gives you one bond carbon proton coupling. So you draw from the center of this, you draw a vertical line, you get carbon and proton chemical shift. Draw a horizontal line, you get carbon chemical shift. This is what the spectrum you get for this isotopomer. What about the other isotopomer? Okay, we will have to see other isotopomer is like this. That is also a doublet, because in the second isotopomer, this is carbon 13. So that gives us a doublet because of coupling with proton B. And this horizontal axis, if you go, you will get carbon B chemical shift, because this is F1 is the carbon 13 dimension. And exactly from the center, you go vertically up. What are you going to get? You are going to get proton B chemical shift. This is what is going to happen now. And again, this separation corresponds to one bond CBHB coupling. This is the spectrum if you are going to get in the F2 coupled HSQC. See, I am in the F1 dimension, we are decoupling, that is okay. Only in the F2 coupled. Now F2 decoupled, we will see what happens. I am doing the decoupling. When I am doing the decoupling, remember I told you in the last class, we are breaking the coupling between carbon and proton in the F2 dimension. That means the satellites will disappear. Okay, we will get only a single peak exact at the center of the doublet, what we saw previously. So you get only one peak. So this is the peak we are going to get. Go horizontally, you get carbon chemical shift. Go vertically, you get proton chemical shift. This is carbon chemical shift, this is proton chemical shift. Okay, that is all. What did we do here? We are breaking the coupling in the F2 dimension. Of course, in the F1 dimension already it was decoupled, there was no coupling. As a consequence, when you do the decoupling in both the dimensions, you get a single peak, single cross peak. Just go horizontally, you get carbon 13 chemical shift. If this is the heteronuclear, this dimension corresponds to carbon 13 or any other X nuclei, and in this dimension, if you go vertically, you will get proton chemical shift. This is the F2 coupled HSQC spectrum of this hypothetical molecule. Now I can extend this molecule. I can do one more thing. I can also see proton-proton couplings in HSQC spectra. Please remember, when I discussed the proton analysis, I also told you by looking at the carbon 13 satellites in the proton spectrum, I can also get homonuclear couplings We took several examples of that. Similar to that, what we will do is we will take the hypothetical molecule like this. What we did, we have extended the molecule by adding CH and CH2. Don't worry about whether this molecule exists or not, it is a hypothetical molecule. Okay? We have taken this molecule. So, what we are going to do now? If I look at the HA, what is the pattern I am going to get? If you look at HA, this carbon, like previous example, it will be a doublet because of coupling with proton and carbon. But what about HA? Remember, this HA is coupled to two equivalent protons. What does it give? This proton-proton coupling will make it a triplet. Okay? So, it is going to be a triplet. Similarly, if you go to HB, this will be a doublet because of this. CH proton coupled to this one makes it a doublet. Okay? Let us look at the spectrum. How do we get? In the 1H NMR spectrum, if I take proton NMR spectrum, carbon A is split because of HA into a doublet and appear as satellites. Look at the proton, carbon A splits this proton and we get satellites. That is what we saw when we analyze the satellite spectra. But this satellite also has coupling to this and each of them will be a triplet. This is what we observed and we analyzed and got the HH coupling from the satellite spectrum. This is what happens. Each line of the satellite doublet is further split into a triplet because of coupling with CH2 proton. Okay? This is the situation. What about the other one? If I look at this CB now, the CB carbon splits this HB proton into a doublet because of one bond coupling and appear as satellites. But what happened? This proton is further split into doublet because of this. This HH coupling appear in the satellite spectrum. So, this each line of the satellite is again a doublet because of HH coupling. So, each doublet is further split into doublets because of coupling with CH proton. This is how the pattern should come for this molecule. Now, let us look at the spectrum. Exactly what we saw. Remember earlier in the coupled HSQC when we saw that along this axis is Ca, that remains same. At the center was HA, chemical shift, that is also same. From center of this to center of this was one bond JCH, that is also same, there is no change. Additional thing is this peak is a triplet, each of the singlet in the doublet of satellite pattern is a triplet because of coupling with CH2 protons. That is the only difference. As far as the interpretation is concerned, center of this gives a proton chemical shift, go along this axis gives you carbon chemical shift for of this group Ca. Okay. What about the other region? And of course, we can easily measure the couplings, HH coupling and CH coupling easily. Okay. Now, this center is HA and this separation is JHH and one bond separation is from any of this peak to identical peak. If you take another triplet, this to this or this to this, if you take, it is going to be one bond carbon proton coupling. Okay, we will go to the CB. CB from the center, if you draw a horizontal line, its carbon chemical should be, and from the center you are going to get proton chemical should be. There is no difference at all. Only thing is the satellite was a doublet, but each line of the satellite is split into doublet because of coupling with CH proton. That is all what happened. Earlier it was exactly at the center of this we got two satellite peaks. Remember, without HH coupling. Now, because of HH coupling, each of the satellites peak is a doublet, and that is what is reflected here. So, this again, if you analyze this spectrum, what are you going to get? You are going to get one bond coupling here and three bond proton-proton couplings. Okay. And if I do the decoupling of that, what you will get? I am breaking the CH coupling, but HH coupling remains same, and this will give me HH coupling, CH coupling is broken. From the center of this again is HA and other is Ca. Here also two doublets will disappear and you are going to get only one doublet. This will be a doublet because of coupling with this proton. This is F2 decoupled HSQC. Remember, I am decoupling here. Okay, this gives you 3GHH. And of course, you may ask me a question, what happened to these groups? I was only concentrating on these two groups. What happened to those groups? That also we can understand. If I look at the terminal groups, we have CH and CH2. And what will happen to the CH2 in the F2 coupled HSQC? Very easily you can understand. Of course, you are going to get a cross peak, 2 doublets. Why 2 doublets? Because this CH2 I am looking at, this will have 1 bond coupling with this carbon and proton. That is this one, 1 bond coupling. Either of them, whether you measure from this peak to this peak or this peak to this peak, is a 1 bond carbon proton coupling. Each of these satellite in the proton spectrum is a doublet. Why? Because it is coupled to this proton. So, CH2 appear in the F2 coupled HSQC appear as doublet of doublets, and the large doublet separation correspond to carbon proton coupling and the small doublet separation correspond to HH coupling. We go to the CH group now. Identical pattern we are getting here also. Why? Because I am looking at this carbon, this is a 1 bond carbon proton coupling, and this carbon, this proton is split into a doublet because of this. That is why this peak also, this cross peak for this CH also appears as doublet of doublet. This is what it is. Separation of any of these peaks from identical peak, if you consider for each of this doublet, either from here to here, it is not, it is from this peak to this peak or from this peak to this peak, then we are going to get 1 bond JCH, and this separation correspond to 3 bond JHH. Either of them is possible. Okay, this is what it is. So, I have taken from center to center here, here also, that also will do, or peak to peak you take for measuring HCH couplings. So, this is how we are going to get for the terminal groups F2 coupled HSQC. Obviously, next is F2 decoupled. What are you going to get for F2 decoupled? You are breaking this coupling. So, exactly these two will come, a doublet will come exactly at the center like this for both of them. Because I am breaking the CH coupling, I am retaining the HH coupling. So, center of this correspond to chemical shift of CH2, center of this here correspond to chemical shift of CH, go horizontally here, you get carbon chemical shift, go horizontally here, you get carbon chemical shift of these groups, terminal groups. Okay. So, we know how to interpret the F2 coupled and F2 decoupled HSQC spectra, how we get the peaks in some hypothetical molecules which you took both, and of course, F1 is always decoupled, I did not explain that, but otherwise similar way we can get coupling between proton and carbon in the F1 dimension. In all these examples I took, F1 is assumed to be decoupled, only F2 side, F2 dimension I took example of decoupled and coupled HSQC. Alright, we will take realistic spectrum of this molecule. This is spectrum of ethyl acetate, it is a realistic spectrum, and you know each of these peak is expanded here, this peak is expanded here and these two is expanded here. Now, our challenge is to identify and assign which is which, and this separation is 1 JCH and this separation is 1 JCH, this separation is 1 JCH. How do you assign these peaks? Of course, obviously you know that the terminal groups must be a CH3, it is a triplet, it should be coupled to CH2 because of CH2, and this CH3 is not coupled to anything, is a singlet. So, easily I can assign the proton peak, there is no doubt about it. But if you see carefully the analysis, if you analyze the multiplicity pattern, it is the F2 coupled HSQC. Now, when I expand this, I will see this peak is doublet of triplets. Why it is doublet of triplets? Because the doublet large separation is coming because of 1 bond carbon proton coupling, that is huge, about 126 hertz, that is a doublet. But each line of this doublet is split into a triplet because of this proton, because this proton is split into this, split this CH3 proton into triplet. As a consequence, satellite pattern appears like 1 to 1 triplet, you see 1 to 1 triplets here. So, this pattern is doublet of triplets. Fine. What is the next one? If you see the next one is, if I consider this one, Very easy to interpret. Last one, green one. Why? I have chosen this to be CH2 group because from the multiplicity pattern I know this is CH3 and this is CH2, this is isolated CH2, isolated CH3. Okay, what is this pattern? How do you interpret that pattern? It's very easy. Of course, this CH2, one bond coupling will be a doublet. This is what you are going to see, one bond coupling. Further, these two CH2 protons are split into quartet because of the CH3 protons. So, each line of the doublet, that satellite, will be a quartet of intensity 1331. Exactly what you are going to see here. If you carefully see here, you get 1331 and 1331 two quartets. Very clear. So, you can interpret that. So, this separation gives me one bond, this coupling, and this separation of any of these adjacent peaks in the quartet gives me HH coupling between this and this. Same thing of course you get here also. Then what is left over? Left over is only this peak. This peak is a doublet, simply just a doublet. An expanded version is seen here. It is a doublet. Why? This carbon has one bond coupling with proton and there is no other proton nearby to couple to it. These are all very far away, 1, 2, 3, 4, 5 bonds away. There is no coupling. As a consequence, this this CH3 attached to the C double bond O is simply a doublet, this CH3 group. You may ask me a question, why I am not seeing the peak for this? Remember, in all the correlation experiment, carbons which are attached to proton only give correlated peaks, cross peaks. Quaternary carbons, CO carbons like this will not give any peaks. As a consequence, you are seeing only 3 peaks and this carbon is missing. How do we get that carbon? That is another experiment HMBC we will discuss today if possible after some time. So, this is how we can get all the coupling information. Okay? Very easily. The same thing if I do the decoupled HSQC. What are we going to do? We are removing CH couplings and only HH couplings are retained. What will happen now? The realistic example. There were doublet of triplets we saw it, earlier. Now that doublet, large doublet is a one bond CH coupling that is broken. We are removed because of decoupling. So, what we are going to see only HH coupling, this one, this CH3 is a triplet because of this. Similarly, this is a quartet because of this. You can identify that. Similarly, this is just a singlet. CH coupling is broken, no HH coupling here. Very easily, you can interpret both coupled and decoupled HSQC spectrum of this molecule. I hope you are all with me or understanding what I am telling. Very easily, you can understand. It is a realistic example of a molecule where we have both coupled and decoupled HSQC, and I said in the decoupled HSQC you get only HH couplings if there exists. In the coupled HSQC you will get both CH coupling and HH coupling if there are HH couplings, and this is what it is, you get only that. And this HSQC experiment we can also do what is called multiplicity edited HSQC. What do you mean multiplicity edited? Remember, if you know the depth experiment, if you remember what we discussed, you have depth 45, depth 90, depth 135. Remember I said depth 135 if you do, we can see that CH2 protons are all negative, CH and CH3 are positive. There we could identify all the CH2 carbons in a crowded region. Why can't we do that? Why can't we bring in this depth sequence, apply with the depth 135 pulse in the middle so that we can also get this correlation plus identify because of the signs whether it is carbon attached to odd protons or carbon attached to even protons. We can do that. Especially for identification of the CH2 carbon, it is very easy because carbons attached to odd protons when CH 135, depth 135, we saw that it is going to be negative in intensity, whereas CH and CH3s are positive in intensity, and this is how it is. So, in the basic 2D, in the 2D HSQC peaks always produces cross peaks which are in phase and positive. They are always in phase signal. in the HSQC experiment. The cross peaks are always in phase and positive signal. If you combine this with depth 135, then we can have different carbon. Cross peaks for this odd attached protons, carbons with odd number of protons attached like CH3 and CH gives us the positive peak, whereas CH2 carbons gives negative peaks. This is what we are going to do. And this is what is called a multiplicity edited HSQC experiment. We can bring in multiplicity editing in the HSQC. This is what we are going to do. This is editing delay, we have to adjust for according to 1 over j, that all we know, delay we have to adjust for 1 over j, and finally when we are going to do 135 degree by putting this editing, we are going to observe all CH2 is negative, all CH and CH3 is positive. The rest of the things remain same. This is polarization transfer, proton to carbon, taking back from carbon to proton and then detecting that proton while doing decoupling of carbon. Other only this portion is extra in this. So, we will do that. The same experiment, same molecule will take. If we do multiplicity edited, ME means multiplicity edited. Multiplicity edited F2 decoupled HSQC, if you consider, see here it is a quartet because CH coupling is broken, we are going to get HH coupling for this CH2 is a quartet because of this. But because also it is a CH2 carbon attached to even number of protons, this is negative in sign. See, this is positive means black color is positive, red color is negative. That is a convention we are following here. So, that means look at the CH3 carbon here, this is positive, this is a CH carbon here, I am sorry, this is also CH3 carbon, that is also positive, whereas this is CH2 carbon is negative in intensity. So, you can identify CH2 carbon here very easily just by plugging in editing sequence in the HSQC. That is what we did here, and this is what it is. These two are positive, other is negative. And if I take the decoupled HSQC spectrum of the same 3-heptanol other molecule, remember this was ethyl acetate, we will take it heptanol, this is the molecule. What do we expect if you do this one? Very clearly you can identify this is of course terminal group H7, that is a triplet, and this is triplet of this is quartet of triplet, again triplet of triplet, triplet of triplet, triplet, and this triplet quartet, all those things we can know that quartet, triplet, everything. Looking in the molecular structure we could assign all the protons here. Remember we analyzed this also in the proton NMR spectrum when we analyzed. So, what do we do here? We know a proton here, go along this axis, of course this is where you identify, go vertically along this axis, you get proton chemical shift, come horizontally you get carbon chemical shift for this. For this CH3 carbon, it is here, this is the proton chemical shift, this is carbon chemical shift. So, carbon and proton chemical shifts for this molecule can be assigned very easily, you can obtain it very easily. But then we will expand this in the decoupled version, then you will see very clearly all this multiplicity. Here you see this is a triplet, this is a triplet, this is a quintet, this is a quintet, this is a quartet, and there are two peaks overlapped here H2 and H4, and H2 is a triplet, H2 is a quartet and this is a triplet H1. See this quartet is there H2 and you see they are well separated out. Remember, if I look at the proton spectrum it looks jumbled up, whereas in the carbon 13 dimension by using carbon 13 chemical shift I could separate out the multiplicity, I can resolve the multiplicity very easily. I know what is quartet here 1331 which is difficult to extract from this. I can easily measure the J coupling here very easily. So, this is the expanded version of that, and you go along this axis very easily like I said earlier, you can get carbon chemical shifts here, you go like this you get proton chemical shifts, everything is done. Same 3-heptanol, if you do multiplicity edited me-HSQC if you do, what do you expect here? 1, 2, 3, 4 CH2s are there. That means 4 peaks should be negative intensity and these terminal CH3s, 2 of them should be positive. There are only 7 carbons, CO carbon does not give signal. After the 6 carbons, 4 should be negative in intensity and 2 should be positive. Look at it, this is red, red, red and red. This tells me all CH2 carbons are here, okay, and these must be CH3 protons, CH3 carbons here. This is proton chemical shift, carbon chemical shift. So CH3 carbons are identified and CH2 carbons are identified based on the signs. One has negative intensity, other has positive intensity. You may say color code is like this. That is the way it is followed. If you take the cross section here in the HSQC experiment and plot individual cross sections like this, each of them I can take this cross section and plot it. You see, this is positive intensity, this is negative, all are negative. This tells me these are all CH2s. The same thing instead of plotting in the stick plot, nowadays we do not plot the stack plot. So in the contours, the color is different. These are all positive, these are negative colors. That is what we are going to see. We can look at this molecule, another molecule, 400.13 megahertz, multiplicity edited HSQC spectrum of 2-methyl-1,3-heptanol. The same heptanol was there, another methyl group is added here. Like it is similar to the previous molecule. Now what is that you are going to get? Earlier we had 4 CH2 groups, now we have only 3 CH2 groups. So 3 CH2 groups are positive, they are negative intensity, and the rest are all CH3, 1, 2, 3. These are all positive. Odd proton attached. This is the multiplicity edited HSQC of the different molecules. Like other previous molecule, one CH3 group is attached. That's what. See, now you can identify which are CH2s and which are CH3s easily. Okay, let us start analyzing one or two decoupled HSQC spectrum. Very multiplicity. Take this ethyl 3-chloropropionate molecule. This is decoupled multiplicity edited HSQC. And of course, there are, you can find out 1, 2, 3, 4 protonated carbons, one CO carbon, that will not give signal. You will see only 4 peaks are there, out of which 1, 2, 3 are CH2 and 1 is CH3. Obviously, in the multiplicity edited, you are going to get 3 negative and 1 positive, exactly what it is. And of course, from this you go up and identify that was CH3, and of course, this is CH2 which is attached to Cl. You can get this proton chemical shift and carbon chemical shift like that. Okay, very easily you can identify all the proton. This is the proton which is C4 attached to COO. This is the CH2 3 which is attached to this one, chlorine, it is here. So all easy assignment of the HSQC spectra is fairly simple. All you have to do is, if you get the decoupled experiment, do preferably multiplicity edited experiment where you can identify all the carbons and their chemical shifts also attached, proton chemical shift and carbon you will get. Also you will identify CH2 carbons like this, very easily you can do that. So this is a 600 megahertz HSQC spectrum of 4-methoxynaphthaldehyde. Look at this one very easily. This is a phenyl group I have taken. There are 2 protons here, and of course these are all the quaternary carbons. These are 2 which are attached. Looking at the multiplicity pattern, each of them is a doublet. I know these are H2 and H3 proton. Remember, this molecule we also analyzed when we analyzed the proton spectrum. In the phenyl proton spectrum of the aromatic carbons, we analyzed that. And from this you can see that this is proton chemical shift and this is carbon chemical shift. We have the knowledge of assignment from proton. This is carbon 2 and this is carbon, this is proton 2, this is proton 3. Similarly, for other group we can assign. So like this we can keep on assigning n number of this thing. We will take another 1 or 2 example in the next class. Now the time is getting up. What I am going to stop here. I will explain some more examples in the next class, and then we will do something more about HSQC and then switch over to HMBC. So what we did this today, we understood how do we get the cross peaks in the HSQC. We took hypothetical molecules with 2 different carbons present attached to CH2 or CH, does not matter. We saw that 1-1 coupling in a decoupled experiment and coupled experiment. In the coupled experiment we get 1-bond CH coupling in the F2 dimension, and then in the decoupled experiment at the center you are going to get a single peak. CH couplings are broken. Go vertically up you get proton chemical shifts, go horizontally you get carbon chemical shift. That is what we analyze everything. Of course, we extended the molecule and we saw that, like we saw in the proton NMR spectrum when we analyze proton NMR spectrum of satellites, we also get HH coupling that get reflected. So in the decoupled version and coupled version of a molecule containing different protons, more number of protons. The carbon which have remote coupling, CH carbon, let us say carbon attached to proton. If those protons are coupled to remotely bonded other protons, that coupling is also reflected in the satellite spectrum. So that also we saw, and we took the example of realistic example of the molecule to analyze the spectrum, especially multiplicated, where we can put in depth 135 sequence in the middle to identify CH2 carbons which are negative in sign, whereas CH and CH3 are positive, and took one or two example to interpret the spectrum. So with this I am going to stop here. We will continue further in the next class. Thank you.